In our very last lesson of this unit, we are going to talk about how we can incorporate some of this new math back into stoichiometry. So, just a reminder about stoichiometry. Stoichiometry involves calculating the amounts of reactants and products in a chemical reaction. Stoichiometry problems in solution chemistry involve a few additional steps. Some problems may require you to calculate the amount of a reactant given the volume and concentration of the solution. So we can go from concentration and volume to amount, meaning moles, right? And as you recall, um, moles are what we need in order to go from one uh, either reactant or product in a chemical equation to another one. So, so before we learned about how to go from grams to moles, and that works if you have a pure substance, right? If you have a solid or a liquid that's a pure substance, you can get to moles by using um, the molar mass. Okay, but for solutions, we would have to use the N equals C times V to get the moles. So stoichiometry solution only differs in how the moles are calculated. All of the other steps are the same. The general strategy for solving stoichiometry problems is so if we are given a concentration of volume, we can turn that into moles, right? So we're given C and V, and then we convert them into N um, by using the N equals CO times V formula, okay? And then we can, once we are have gotten the moles of our given substance, we can go to the moles of the substance that they want, right? Which is the moles of, so we say the moles of the required substance, and then we can use um, the N equals C times V calculation again to get either um, to get concentration or volume, or if we want to know, for example, the mass, we can use the molar mass. Okay, so we can go from moles to grams and grams to moles, or we can go to from moles to concentration or volume and back. Let's take a look at a question. It says 415 milliliters of a 1.0 mole per liter hydrobromic acid solution is poured over excess zinc metal. Calculate the mass of zinc bromide formed. Okay, so the first thing that we're going to do is find the moles of HBr. So that's the hydrobromic acid. So what we're going to do is figure out what they've given us. They've given us a volume, which is 415 milliliters, and they've given us a concentration that is 1.00 moles per liter. Now, the problem is that they've given us the volume in milliliters, so we would need to convert that to liters. And we know that 1 liter is 1,000 milliliters. So we will end up with 0.415 liters. Okay, so then we can use the N equals C times V. So the concentration is 1.00 moles per liter. and the volume is 0 0.415 liters. So when we multiply this, we know that we have 0.415 moles. Right? That was easy. I don't like the way that looks. Let me erase it. So now we know that we have moles of hydrobromic acid. Now, we need to determine the amount of moles of zinc bromide. And it says use the mole ratio. So to do the mole ratio, we need to know the balanced equation. So let's let's come up with the balanced equation. And let's do it in a different color. Okay. So we know that we have added hydrobromic acid over zinc metal, and we get zinc bromide and hydrogen. Got to put the state there. And so zinc bromide would be aqueous. And then we get hydrogen gas. So, right, this is a single displacement reaction. So this is not balanced. In order to balance it, we would need to put a 2 in front of hydrobromic acid. And now we have 2 hydrogens on the left, 2 hydrogens on the right, 2 bromines on the left, 2 bromines on the right, and 1 zinc on the left, and 1 zinc on the right, and everything is balanced. So it says determine the moles of ZnBr2. So we're going from, right, we're going to go from moles of HBr to moles of ZnBr2. So we know the moles of that we have of HBr, and we would need to multiply it. We get 1 mole of ZnBr2 for every 2 moles of HBr we use, right? And that's just from the coefficients. And then so we're going to end up with half, right? So that would be 0.2075, right? But we need that to 3 significant digits. So 0.208 moles of ZnBr2. And then we need to determine the mass because we're going to the mass, so we need the molar mass. So the molar mass of ZnBr2. So we would need to know the molar mass of zinc, which is, looking it up on my periodic table, 65.38 moles, or sorry, grams per mole. Plus, I have 2 bromines, and each bromine is 79.90 grams per mole. So if I add those together, I get 225.18. and that's grams per mole. So to find the mass, right, I have 0.208 moles of ZnBr2 times 225.18 grams per 1 mole, and I would get 46.83744 grams, right? Let's do three significant figures. So 46.8 grams of ZnBr2 is what mass I would expect. Okay. Example 2, calculate the amount of calcium carbonate produced when 250 milliliters of, so that's a volume of 0.20 moles per liter, that's a concentration, solution of Na2CO3 is reacted with excess CaCl2 solution. So our balanced equation, we have Na2CO3 aqueous plus CaCl2 aqueous. This is going to be a double displacement reaction. So then we would get NaCl, which is going to be aqueous if I look it up on my solubility table, and CaCO3, which is going to be my precipitate. Okay, so this asks for the amount of calcium carbonate, right? So I'm going to leave it in moles, right? Usually amount means moles. Let's check. Is my equation balanced? No. I have 2 sodiums on the left and only 1 sodium on the right. So I'm going to put a 2 there. I have 1 carbonate on the left, 1 carbonate on the right, 1 calcium on the left, 1 calcium on the right, 2 chlorines on the left, and 2 chlorines on the right. So everything is balanced. So number 1, right, we are going to find the moles of Na2CO3. So we're going to use N equals C times V. Okay, 250 milliliters is 0.250 liters. So actually, do I have room for this conversion? Oh, here, I'll do it up here. So our volume is equal to 250 milliliters, but that's not a good unit for us. So we would multiply it by 1 liter over 1,000 milliliters, and we get 0.250 liters. Okay, so 0.20 moles per liter times 0.250 liters gives me 0.05 moles. I want to make sure there's a 0 because it gets to have 2 significant digits. So we have moles of Na2CO2, 3. So they want us to find the amount of calcium carbonate. When you see amount in chemistry, it means moles. Okay, so all we have to do second is we just have to use the molar ratio. So 0.050 moles and then we're going to just use the balanced equation. So we get 1 mole of CaCl, sorry, CaCO3, right, calcium carbonate, per 1 mole of Na2CO3. So we're going to get the same amount. We're going to get 0.050 moles of CaCO3. That's it. Okay. If they had asked us for grams, right, we would multiply them by the molar mass. Right? If they had asked us for volume, we would have multiplied by the concentration. Okay. Limiting reactant problems. Okay, this is probably where if you're feeling stressed about life, like maybe we don't have to do this. But I'll show you how to do a limiting reactant problem that involves concentration and volume. It's really the same steps as before. It says 15.5 milligrams of, 15.5 grams of magnesium is reacted with 25 milliliters of a 1.05 mole per liter hydrochloric acid solution. So one of these things is in grams and the other one is a solution. Determine which is the limiting reactant and the mass of hydrogen gas produced by the reactant. So the step number 1 is we are going to determine the moles of reactant. So I'm going to put a little divider. This side is going to be magnesium. This side is going to be HCl. Oh, before we get to that point, let's do the balanced equation time. So we have Mg solid plus HCl aqueous, and then we have to predict the products, right? One of the products we know is hydrogen gas, and the other one, this is a single displacement reaction. So the magnesium is going to displace the hydrogen, and we are going to get a compound, right? What compound? Well, we're going to get a compound that has magnesium and it has chlorine in it. So do a little crossover rule, and we know that we are going to get MgCl2, aqueous. Let's check this equation. It is not balanced because there are 2 hydrogens on the product side and only 1 on the reactant side. So I would need to put a coefficient there. And then I think everything is balanced. So we have 2 chlorines on the left, 2 chlorines on the right, 2 hydrogens on the left, 2 hydrogens on the right, 1 magnesium on the left, and 1 magnesium on the right. Okay, step 1 says, to determine the moles of the reactants, magnesium is given to us in mass. So we have to go from mass of magnesium to the moles of magnesium, in which case we would need the molar mass. So we have 15.5 grams times, and we want to use the molar mass with the 1 mole on top and the molar mass. Magnesium doesn't need a calculation. We just need to look it up on the periodic table. The periodic table, the molar mass of magnesium is 24.31 grams. Okay, put that into the calculator. 15.5 divided by 24.31 gives me 60. Let's see, I need 3 significant figures. So 0.6375. So 638 moles. Okay, same for HCl, but HCl we're going from concentration and volume of HCl to the moles of HCl. So we have to use N equals C times V, which is, so the concentration is 1.05 moles per liter. And then 25 milliliters we would need to convert that to liters. So we know that 1 liter is 1,000 milliliters, and then we're going to get 0.0250 liters. Put that in. Hold on, something's gone a little wrong with my calculation. 1.05. Oh boy. 1.05 times 0.0250. Okay, and I will get here 0.026 262 moles. Okay, so we are going to determine the moles of hydrogen gas each one would produce. So, for magnesium, we had 0.638 moles, and I know that I produce 1 mole of hydrogen for every 1 mole of magnesium I consume. So I will get here 0.638 moles of hydrogen. And then I'm going to do the same thing for hydrochloric acid. So I have 0.0262 moles. And for every, I produce 1 mole of H2 gas for every 2 moles of HCl. So I would get here 0.0131 moles of H2. Okay, compare. HCl is our limiting reactant. Because it produces less. And we make 0.0131 moles of H2. And then the last thing that we have to do is we have to convert our moles of hydrogen produced into grams. So we made 0.0131 moles of H2, and then we would have to multiply it by the molar mass. and we would get 0.0265 grams of hydrogen gas. Okay, so that is really the end of things for uh, solutions and solubility. So now you know how to do stoichiometry with something that is a solid or liquid that has a mass, and for something that is in an aqueous solution.